Okay, good afternoon, everyone. Maybe we can start. Could you please press the thumbs up sign if you can hear me? Okay, so thank you very much. Good afternoon and welcome to the second IMath webinar for this semester. I am Gino Angelo Velasco, Coordinator for Research of the Institute. Okay, so before we begin, let me remind everyone that this webinar is being recorded and it is being streamed live on YouTube. So the link can be found on the official IMath Facebook page. Okay, so maybe we can start. The speaker for today is Dr. Kenneth De La Rosa of the Matrix Analysis and Linear Algebra Group of the Institute. So he recently finished his PhD from Drexel University, and today he will present his work with Hugo Verdeman titled Completing an Operator Matrix and the Free Joint Numerical Radius. Okay, so let us all welcome Dr. Kenneth De La Rosa.
Hello. Nadidinig ako.
Yes, nadidinig po namin kayo, Sir Kenneth.
So let me just set this up. So nakikita po yung screen.
Yes, we can see the screen.
Okay. I guess I'll start. Yeah, hello. Good afternoon to everyone. I'd like to thank the Institute of Mathematics for having this webinar and allows us researchers a venue to share our research despite the ongoing pandemic. Salamat kay Sir Gino, for organizing this. And thank you all for coming to today's talk. So I'm Kenneth De La Rosa. I'm representing the Matrix Analysis and Linear Algebra Group of the Institute. So hopefully mabigyan ko ng justice. I'll be presenting one chapter from my dissertation, and it's about completing an operator matrix and the free joint numerical radius. So this is joint work with my advisor, Professor Hugo Werdeman from Drexel University, Philadelphia. So I'll go ahead and start. Here's an outline of my presentation. I'll start by introducing some definitions. I'll state the theorem that I'd like to prove. Then I'll discuss matrix completion techniques that help us prove the theorem. And with that machinery, we'll prove the main result. After proving the main result, it turns out that that implies another problem. So to understand that problem, I'll be needing more basic properties of the free joint numerical radius. And in the context of that new problem, I'll consider generalized permutations and prove miscellaneous results about these special matrices. I'll end by mentioning some numerical stuff and some open problems. So let me begin with some definition. Given a bounded Hilbert space operator, its numerical radius is defined to be the supremum of the absolute value of inner products of the form XHH, where H is a unit vector in the Hilbert space. So this is the radius of the smallest circle centered at the origin that contains the so-called numerical range of the operator X, which is defined as the set of all scalars of the form XHH, where H is a unit vector of the Hilbert space. For some examples, if the operator is this 2x2 matrix 0, 2, 0, 0, it can be shown that its numerical range is the closed unit disk. If the operator is the forward shift on little L2, it can be shown that its numerical range is the open unit disk. In both cases, the numerical radius is going to be 1. Okay. So these examples show that in general, the numerical range may or may not be open or closed, although in finite dimension, it's going to be closed. What we can say in general is that the numerical range is a convex subset of the complex plane. So this is a well celebrated result in this area. It's attributed to Toeplitz and Hustler. I'll also mention two properties that have become useful in applications. One is the spectral inclusion property, which is this. It gives us an estimate of where the spectrum is, provided that one knows where the numerical range is. The other property that I'd like to mention is this subadditivity property satisfied with the numerical range. And how can one use this in applications? If you think of x plus y as some sort of perturbation of x by y, then this tells us an estimate where the numerical range of x plus y is, knowing the numerical ranges of x and y. And as a side note, if you replace the numerical range by the spectrum and consider the analogous inclusion, surprisingly, that's going to be false. Okay. So one classical result in this area is due to Ando, where he gives a matrix positivity characterization of the unit ball in the numerical radius norm. So in particular, given a Hilbert space operator X, its numerical range is at most 1. That's equivalent to the existence of a self-adjoint operator such that this 2 by 2 operator matrix is positive semi-definite. So in this context, that's what I'm denoting positive semi-definiteness by a greater than or equal symbol. And it's easy to see by just a change of variables that condition 2 is equivalent to condition 3. That is, there are operators A1 and A2 that add up to the identity for which this 2 by 2 operator matrix is positive semi-definite. So I want to rewrite Ando's result in a particular way. I want to replace the equalities here by strict inequality. And I want to replace x by 2x. So if I remove instances of equalities, so the first condition will now be strict inequality, the second condition will now be strict inequality, and in this context, this is what I'm denoting positive definiteness. And similarly here. Okay, I also replace x by 2x, and the consequence of that in the first condition is now it's going to become numerical radius less than 1/2 instead of numerical radius less than 1. If I replace x by 2x in the second condition, we have this modified condition 2, and then if I replace x by 2x in the condition 3 in the previous slide, it's gonna become this condition. Notice that this condition on the A's doesn't change. So I do prefer this formulation of Ando's result for what we will do today. Any questions so far?
Questions? Okay pa naman, sir?
Okay, so in certain areas of mathematics, like analysis, it's natural to consider multivariable extensions of certain concepts and results. I guess the simplest example of this is multivariable calculus. So in the institute, that's Math 23. So there's a similar theme in operator theory, where one would like to extend standard results in the multivariable setting. So in particular, Arenik, Kavruk, and Paulson in 2013 considered extending Ando's result to the multivariable setting. And so that everyone can anticipate what that generalization is, I'm highlighting conditions 1 and 3 so that you can easily compare. So what is this multivariable generalization? It goes as follows. Given our M operators, the following are equivalent. Something is less than 1/2. That's equivalent to the existence of M plus 1 operators that add up to the identity for which this M plus 1 by M plus 1 operator matrix is positive definite. Okay, I'd like you to focus on condition 2 first. In a way, this is somewhat the natural extension of condition 3 in the previous slide, right? When M equals 1, when there's only one operator, there are, in the previous slide, there are two operators, M plus 1 equals 2 when M equals 1, such that they add up to the identity for which a certain 2 by 2 operator matrix is positive definite. That begs the question, what is this less than 1/2 condition? Well, that's saying that the so-called free joint numerical radius of the tuple x1 to xm is strictly less than 1/2. And what is the free joint numerical radius of a tuple? So given our m operators, x1 to xm, the free joint numerical radius of the tuple x1 to xm is defined to be the supremum of the numerical radius of operators of the form x1 tensor u1 up plus and so on plus xm tensor um, where the supremum is taken over all Hilbert spaces k, and for all choices of m unitaries in B of k, and the tensor product is spatial. So as you probably expect, when there's only one operator, and when m equals 1, the free joint numerical radius coincides with the classical one. And theorem 3, the multivariable analog to Ando's theorem, when m equals 1, it reduces to Ando's classical result. Okay. So the general goal of this talk is to pursue different aspects of Ando's result in this more general setting. I'll get more specific later on. There are comments in the chat. So let's go back to condition 2 in theorem 3. And that's the condition that there are m plus 1 operators adding to the identity for which this certain block tridiagonal operator matrix is positive definite. Let's give this a name. Let's call it gamma of A1 to AM plus 1, where the inputs A1 to AM plus 1 are the diagonal entries of this block tridiagonal operator matrix. Okay, so one natural question is how to solve for these A1 to AM plus 1 such that this condition holds. And it turns out if we know a solution to a slightly different problem, then we can easily identify A1 to AM plus 1. So initially we have this multivariable problem, and what we'll see is it's enough to solve a single variable problem. No? Okay. And this equation, we can view this as a fixed point equation. So I'll give the right-hand side a name. I'm gonna call it f of L. And to be more precise, given our M operators, let's consider a positive semi-definite Z. We'll define its image under F to be this expression. Identity plus expressions of the form like this and like this. Okay, so the result that I like to prove is the following. Given M operators such that the Hilbert space is finite dimensional, the following are equivalent. There exists a positive definite fixed point of F, sorry, that's equivalent to the condition that the free joint numerical radius is strictly less than 1/2. That's the claim. I'll pause for a moment. Any questions so far?
questions po from the audience so far. If you have anything to clarify, just feel free to type in your question or you may raise your hand. Question po. So yeah, sir, maybe you can continue.
Okay, so the next part involves results that show why the fixed point equation naturally arises from a certain completion problem. So I'll start with the following proposition. Given M operators, such that the dimension of the Hilbert space is finite, suppose there's a solution to condition 2 in theorem 3. Suppose there are M plus 1 operators that add up to the identity for which the block tridiagonal operator matrix with A1 up to AM plus 1 as diagonal blocks is positive definite. So suppose you can find such a solution. So the conclusion is there's going to be a unique solution, A1 to AM plus 1, with an additional property that in the inverse of gamma, the diagonal blocks are all equal. And we can further characterize this solution as the unique maximizer of the determinant of gamma over all positive definite completions. So over all solutions that satisfy these conditions. Okay. So I'll skip the proof, but what I'd like to point out are two things. Spoiler alert, the L that appears in this proposition is the solution to the fixed point problem. And more on that later. So proposition 6, no? So this is the second remark, strongly suggests that we should probably look at operator matrices whose inverse is a block tridiagonal. So with that in mind, let's start with the 3 by 3 case. I think this is a very crucial and informative case. So we first recall some useful facts about 2 by 2 invertible operator matrices. Given an operator A, if the 2 by 2 operator matrix ABCD is invertible, that's equivalent to this condition that this expression is invertible. So this expression is known as the Schur complement of A relative to this 2 by 2 operator matrix. So suppose one has a 3 by 3 operator matrix such that the middle block P22 and this 2 by 2 principal submatrix are both invertible. We can decompose P in the following way. It involves 3 factors. The middle factor, if you take note, there are a bunch of zeros here, and QRST are defined as follows. So Q is this, R is this, S and T. Take note that Q is the Schur complement of P22 relative to this block, and T is the Schur complement of P22 relative to this block. R and S are Schur complement-like constructions. Okay, so let's look at equation 5. By the structure of the first and the third factor, these things are invertible. Hence, P is invertible if and only if the middle factor is invertible. By assumption, P22 is invertible. So it's enough to know that the matrix QR or the operator matrix QRST, that 2 by 2 operator matrix is invertible. So that's this assertion. P is invertible if and only if QRST is invertible. Now, why is this going to be equivalent to that? No. Notice that this is the Schur complement of Q relative to this, right? So that begs the question, why is Q invertible in the first place? But remember, Q is the Schur complement of P22 relative to this block. So by assumption, P22 is invertible. This is invertible by the 2 by 2 remark. This Schur complement has to be invertible. Okay, so we'll assume that P is invertible. Hence, we can invert this formula, no, taking the inverse both sides, will give us something like this. No? The middle factor simplifies to something like this. Okay. Now we'll assume further that the inverse of P, so P inverse, which is equal to this, and the middle factor is equal to this, we'll assume that P inverse is block tridiagonal. So what that means is that the 1, 3 and the 3, 1 blocks are 0. Okay, so because of this decomposition, when you're locating the 1, 3 block, okay, because of this first row, third column, you'll hit this entry, right? So if we assume that P inverse is block tridiagonal, then the 1, 3 entry, for instance, the 1, 3 entry is 0, and the 1, 3 entry of P inverse will hit this if you use this decomposition. If you pre-multiply and post-multiply by the appropriate operators, you'll be able to conclude that R will be 0. No, so that's the conclusion. By definition, R equals this sure complement-like construction, which if you simplify, you get some sort of relationship among the entries of P. And similarly, since we're under this assumption, the 3, 1 entry, third row, first column entry of P inverse is going to be 0. So if you do the same argument, the 3, 1 entry will hit this entry. And if that's 0, by multiplying by the appropriate operators, one can conclude that S has to be 0, and by definition, S is equal to this. And we get another relation among the entries of P. And we can say more. We know that this short complement is invertible, right? Because we're assuming that P is invertible. And under the assumption that P inverse is block tridiagonal, we've seen that S and R are 0. So this actually simplifies to just T, which we know to be equal to this by definition. So that's invertible. Sure. What is this again? This is the short complement of P22 relative to a 2 by 2 block, which is the 2 by 2 block here. So we know P22 is invertible, and we've shown that this short complement is invertible. This has to be invertible. And furthermore, go um, by 6 and 7, those equations earlier, and under the current assumptions, we can simplify P inverse in the following way. We can decompose it as a sum of stuff that depends only on 2 by 2 principal submatrices minus some sort of overlap. So they overlap at P2. So you need to subtract that. Okay. So for the converse, if we assume that the entries of P satisfy these conditions, and if in addition we know that the 2 by 2 principal submatrix indicated here is invertible, then what can we say? We already know that Q is invertible by assumption. That comes from the original set of assumptions. If we're under this assumption now, R and S has to be 0. So we can equate this to 0. So that begs the question, why is T invertible? Remember, we're assuming P22 is invertible. If this is invertible, then the Schur complement of P22 relative to this matrix, operator matrix, is also invertible, and that's exactly T. So this diagonal operator matrix will now be invertible. But if you remember, this is equivalent to saying that P is invertible. And by the formulas earlier, 6 and 7, we can say more. P inverse will be block tridiagonal. Okay. So a few comments before I proceed. Similar assertions have been considered in these papers. Matrices with banded inverses. So for the matrix case, it's considered in this paper. For the block matrix case, it's considered in this paper. And in addition, if we know that the 2 by 2 principal submatrices indicated here are positive definite, then by the equations that we considered earlier, E is necessarily invertible. Necessarily positive definite. And yeah, to those wondering, yes, the 3 by 3 case generalizes to higher sizes. And it's this theorem. Given an m plus 1 by m plus 1 operator matrix, m at least 2, under these invertibility conditions, PII, I from 2 to m are invertible operators, and then these 2 by 2 principal submatrices from 1 to m are invertible, then one can show that P is invertible and P inverses block tridiagonal is equivalent to this set of conditions involving the entries of P. Okay. And in this case, we can decompose the inverse of P as a sum of stuff, of involving 2 by 2 principal submatrices of the original matrix and minus some overlaps. And furthermore, if the matrices in condition 2 are positive definite, so is P. So marami siya, no? So, but what I'd like you to remember is under the right assumptions, we can decompose P as a sum of stuff that depends only on 2 by 2 principal submatrices minus overlaps. Hopefully, maalala niyo yung string of words na yun. So what does this buy us? If we consider this operator completion problem where we consider these diagonal blocks, we consider them to be given. So I denoted them P11 to Pm plus 1, M plus 1. And I will also consider the first super diagonal given by x1 up to xm and the first subdiagonal x1 star up to xm star to be given. And we would also like the completion to be positive definite. So let's consider this operator matrix completion problem. So let's fill in the unknowns. No, these question marks. Let's give them symbols. So here I filled in the unknowns by Pij. The diagonal here I filled in the unknowns by A1 up to AM plus 1. Okay, so what do we have so far? We have something being positive definite, so therefore these 2 by 2, in particular these 2 by 2 principal submatrices are positive definite, and in particular they're invertible. Okay, we have a certain m plus 1 by m plus 1 matrix, operator matrix, whose inverse is block tridiagonal. So that should ring a bell. You have so you have that set up, So this is the right set of assumptions where we can apply that formula earlier, where we can decompose this inverse as a sum of stuff that depends only on 2 by 2 principal submatrices minus some overlaps. And that's basically this slide here, Sulat ko na lang para makita. This we can decompose as follows, and we know that we're assuming that that's equal to this block diagonal, so we can equate both sides. Okay. Since this side is block tridiagonal, and these terms are also block tridiagonal, this equation will imply several 2 by 2 completion problems by just equating this to the corresponding 2 by 2 slots here, and so on. So in other words, that equation, that equality will imply for I from 1 to m, completion problems of the following form, where PII and PI plus 1, XI and XI star are considered given. And this is a 2 by 2 completion problem where we would like the completion to be positive definite. Okay. So such a completion problem has been considered in this paper um, in the setting of matrices. So the matrix version of this 2 by 2 completion problem has been considered in this paper, but the prescribed blocks are not necessarily squares. Pero hindi naman natin kailangan yung full generality. No? We only want certain solution to the 2 by 2 problem where the matrices or rather the operators are going to be positive definite. And one can show a positive definite operator version of the main result in this paper, which will allow us to solve this. I won't show the formulas anymore, but what that modification tells us is that this 2 by 2 completion will have unique solution, and the solution is there's an explicit formula, and it's in terms of xi star and pi plus 1 I plus 1. So we can solve this. So we can solve this, and we have a formula for the completion, and it's in terms of xi star pi plus 1 I plus 1. So what's the upshot? We can solve this if we go back here. If we know how to solve these 2 by 2 things, for example, this first slot, then we can compute for A1 and A2, and so on, and similarly with the other 2 by 2 blocks. In other words, we can write down a formula for A1 up to AM plus 1, those diagonal blocks, in terms of P11 up to PM plus 1, M plus 1, and X1 star up to XM and XM star. That's good. How can we use this? Well, if for some L, we insist that P11 up to PM plus 1, M plus 1 are all equal to that L, which is positive definite, and this AJs add up to the identity, then stuff happens. I'd like to point out that this assumption, this consideration is not so random. We've seen this assertion in proposition 6, where we have this unique solution such that in the inverse of gamma, the diagonal blocks are all equal to L. Okay, so what if we do have such an L such that the P11, PM plus 1, M plus 1 are all equal, and AJs add up to the identity? Well, if we replace P11 up to PM plus 1, M plus 1 here by L, and we add the AJs, and under this assumption that's equal to identity, we can simplify that sum in such a way that we can factor out the following things. We can factor out L to the negative 1/2 on the left, and we can factor out L to the negative 1/2 on the right. And what remains in the middle is f of L. Okay? And that's gonna imply that we've found a fixed point for f. And that's equal to L. Okay, so conversely, what if we start with a positive definite fixed point of f? Let's call that L. What these formulas suggest is if we plug in P11 to PM plus 1 and equate that equal to L, we would like to know what happens to the sum of those AJs and what happens if we plug in those A's to gamma. And it turns out that those A's, so these I got from the previous set of equations by just plugging in P11 up to Pm plus 1, m plus 1. I plug in L, and L is a fixed point of F. Of course, I'll skip the proof now, but one can show that these A's add up to the identity, and more importantly, they make gamma positive definite. And like I said, this requires a proof, which I'll skip. And yeah, we have everything we need to prove the main result. If we start with a positive definite fixed point, if I call that L by the result that I just stated, proposition 8, we can set A1 up to AM plus 1. That will make gamma positive definite. And if we add them, if we add those A's, we'll get the identity. And that condition is exactly equivalent to the free joint numerical radius being less than 1/2, by theorem 3. That's the multivariable analog of Handel's theorem. So that's 1 implies 2. Good. What about 2 implies 1? If we start with this condition by theorem 3, by the multivariable analog, there exists A1 up to AM plus 1 that add up to the identity that makes gamma positive definite. So in other words, there's a solution to the completion problem. And by proposition 6, if you know that there's a solution, that will imply that there's a unique solution such that in the inverse, there are equal diagonal blocks. And we call that L. And by the remark I made earlier about having an L, positive definite L, and equating that to P11 up to Pm plus 1, M plus 1, and under the assumption that the AJs are going to add up to the identity, then that L is going to be a fixed point of F. And that's this conclusion. Okay, so that's the proof of theorem 5. That's good. So the natural follow-up question is how to find such an L. No? If there's an explicit formula for L, it's probably going to be very complicated. So instead, we'll try to approximate L, and we'll consider the following standard iterative scheme where I'm just applying F to 0 k times. In particular, this is going to be the recurrence whose initial value is m plus 1 times the identity, and the succeeding terms are lk plus 1 equals f of lk, all k natural numbers. So here's a conjecture. If you have that recurrence that I just defined, no, then the following are our conjectures. The LKs are monotonically increasing in the Loebner ordering. And in addition, if you have the free joint numerical radius of your starting operators, if that's less than 1/2, then the LKs converges to a fixed point of F. So these are open problems still. Numerical experiments suggest that they are true, but they remain open problems. So in the remaining part of the talk, what I'll do is I'll consider special matrices for which this conjecture will be true. And for that, we need more basic properties of the free joint numerical radius. So for example, given M operators, the free joint numerical radius is invariant under unitary similarity. In the following sense, no, you can insert U star. They have to be in the same. They have to be the same unitary for each component, no, and the free joint numerical radius remains the same. We also have the following lower bounds and upper bounds for the free joint numerical radius. Okay. Now, given an n by n complex matrix, we define its absolute value matrix, and as the name suggests, it's the matrix of absolute values of the entries of x. No, and I denote this by abs x. If you notice, I put quotation marks here because I can't really find a name for this in the literature. So I just give it a name so that we have a point of reference. And word of warning, this is not to be confused with the more standard terminology which is the absolute value of x, which is defined to be this. In general, they might not be equal, these things, but when x is diagonal, they coincide. Okay, so why am I introducing this? One can show that given M complex matrices, the free joint numerical radius of these M matrices is bounded above by the usual numerical radius of a single matrix. No, single matrix that involves the absolute value matrices of these given matrices. And whenever one has an inequality, one natural question to ask is whether the inequality is sharp. To answer that question, we'll introduce generalized permutations. So what is a generalized permutation? Given an n by n complex matrix, we'll call it a generalized permutation if it has at most one non-zero entry in each row and column. So one, at most one. So pwedeng merong 0 row, 0 column. Okay lang yan. And examples, as the name suggests, permutation matrices are generalized permutations. We'll consider diagonal matrices as generalized permutations. Weighted shift matrices are generalized permutations. And to answer the question about the sharpness of the inequality, if we take the tuple of matrices to be generalized permutations, one can show that, well, one can show two things, that the free joint numerical radius of that tuple of generalized permutation is equal to the free joint numerical radius of the absolute value matrices of each. So that's still in the level of free joint numerical radius, but we can simplify that to be the usual numerical radius of a single matrix. So this equality established the sharpness of the inequality that I showed earlier. And as a corollary to this, if one has a family of commuting normal matrices, then the free joint numerical radius of such a family will be equal to the free joint numerical radius of the standard absolute value and can be further simplified as the numerical radius, the usual numerical radius of the sum of the absolute value of each. So the key step here in this corollary is to remember this certain result in matrix analysis, that if you have a commuting family of normal matrices, then you can simultaneously diagonalize that family by a single unitary matrix. And then you apply theorem 12. So going back to conjecture 10, when the given matrices are generalized permutations, then the recurrence defined in 15, one can show that the recurrence is going to be monotonically increasing. So in other words, one part of the conjecture is true for a certain class of matrices. So that's cool, no? If we have some sort of boundedness condition, then we can probably prove the second part, which is the conjecture about convergence. And indeed, we have that in this theorem. So this result involves the trace norm. Let me just define it here. The trace norm of an m by n matrix, that's denoted by this L1 symbol. That's the trace of the absolute value of x. And what does this theorem say? Given n by n matrices, if the free joint numerical radius of such a tuple of matrices is strictly less than 1/2, then the following holds. If I take R, this number R, to be this expression, it's n times n plus 1 divided by 1 minus twice the free joint numerical radius of the tuple, then this conclusion holds. If you have a positive semi-definite matrix whose trace norm is at most R, so in other words, Z is in the R ball of the trace norm, where R is equal to this, then the image of Z under F is also in the R ball with respect to the trace norm. So to prove this result, we need the following lemma, which relates the trace norm and the free joint numerical radius. I'll skip the proof, but what I'd like to mention is that this inequality implies the arithmetic and geometric mean inequality, which I think it's skewed by taking x to be the Jordan block 2 by 2 Jordan block 0, 1, 0, 0, and z to just be x, y, the diagonal x, y, and then applying this result. So with a little more work, and by proposition 14 and theorem 15, one can show that indeed the conjecture is true for generalized permutations. Okay, so for the last part of the talk, I'll just say something about some numerical stuff and some open problems. So we can numerically compute for the free joint numerical radius of a tuple of matrices by interpreting theorem 3 as a semi-definite program. So we can minimize a scalar row subject to this positivity condition and this affine condition. So to solve this semi-definite program, we use CVX. It's a package for solving convex programs and implemented in MATLAB. If you have time, we can probably do a demo. But otherwise, I'll move on to the final remarks. So let me just summarize what I did. Given our M operators, we defined F to be this, and there's a corresponding recurrence relation in terms of this. In theorem 5, we showed that the existence of a positive definite fixed point of F is equivalent to the condition that the free joint numerical radius is strictly less than 1/2. I should note that the proof that I showed actually works for infinite dimensional Hilbert spaces. So the natural question is, what happens to the converse, in the infinite dimensional case? So unfortunately, the argument that I showed of showing 2 implies 1 really depended on the finite dimensionality of the underlying Hilbert space. So the first open problem that I'd like to mention is under the assumption that the free joint numerical radius of the operators is less than 1/2, show that F has a positive definite fixed point. And the other theorem that we proved or mentioned is that given generalized permutations, we showed that the corresponding recurrence is monotonically increasing, and if the free joint numerical radius of the tuple of generalized permutations is less than 1/2, then the corresponding recurrence converges to a fixed point of F. And so open problems 2 and 3 are to show that these statements hold for general matrices or operators. And these are some of the references that I mentioned in the talk. And that's the end of my presentation. Thanks. Any questions?
Thank you very much, Dr. De La Rosa. Let us all give Sir Kenneth a warm round of virtual applause. Thank you. It was an interesting talk. So do we have any question from the audience? Raise lang po tayo ng kamay or you can type it in the chat box. Okay. So actually, may curious question ako. Hindi ko alam kung nabanggit mo kanina sa simula. Kung itong ginawa niyo na on itong sa dito sa case niyo is maibabalik niyo, may version din ba to na kung saan yung numerical radius niyo kagaya do sa original na ando na less than or equal to 1, or magkaka-problema na ba yun in terms of some invertibilities halimbawa? Kasi di ba ginawa niyo less than 1, inan mo siya to less than 1/2 and then
So,
positive definite instead. So may
if
version ba to?
meron naman, sir, pwede siyang i-rewrite in such a way. Kasi basically, you'll just be scaling things. Kung mababago yung gamma, no? But I don't think that I don't think that will affect the problem. Ma-rewrite lang in certain expressions, but the difficulty is still the same. I'd like to remark the reason why they like that version in that paper in Parenik, Kavrok, and Paulsen, bucket strict inequality instead of the usual inequality by Handel. They wanted their result to hold for C-star algebras, no? And kapag ganun yung level of generality, kailangan talaga strict inequality. So, kung yung C-star algebra mo is B of H, okay lang na may equality din. So, lalagyan mo equality sa lahat. But if the starting C-star algebra is not necessarily B of H, then you do have to adjust, no? Although we didn't consider C-star algebras here, although you can probably formulate the same set of questions, no? But we just focus on B of H kasi yung intuition, in a way, mas madali kapag B of H muna.
So, at tapos pala yung sa ano ba, yung sa dun sa numerical experiment yung na ginawa dun sa pag-compute ng numerical radius. Madali lang siyang mahanap. Tipong few iterations lang siya or hindi naman siya
Dito sa MATLAB
yung complexity ng nung sa program nila. So madali lang siyang
in terms of time, mabilis lang. Although hindi ko
so madali lang maghanap ng numerical ranges na.
Yes, sir. Kapag ginamit niyo na yung CTX na to na program. Although hindi ko talaga yan mabilis na siya for what I do. Maybe kung mga sizes ng matrices are 1,000 by 1,000, tapos meron kang 100 na matrices, malaki na yan, sobrang laki na. Baka hindi na kaya ng machine.
Doon sa mga example nyo, ano yung size na mga ginawa nyo so far?
Nitong program na to, very random, maybe 10 by 10, tapos usually nagpo-focus kami sa 2 operators, yung next natural step. At yeah, I think siguro pwede pa siyang, kasi ano lang, no? Pag sinulat yung code, sulat mo siya sa semi-definite program once you write it that way. Kasi talagay mo lang yung given matrices. Invoke mo na yung STP line of CVX, then okay na yun. Although hindi ko tinest kung gaano katagal, like explicitly ano yung time, no? But I think it's fast enough kapag small yung matrices.
So actually very interesting yung conjecture niya, no? Tsaka yung nahanap yung mga examples kung saan siya totoo. So how are you so far dun sa pagpapakita ng conjecture for the general case, or are you still looking into several examples na?
Which
yung
conjecture?
Sa
1 or sa 2, 3?
Yung sa yung sa yung nag-i-imply ng fixed point. So yung sequence of matrices na nagko-converge dun sa fixed point, yes.
So ang question is,
so kumusta na kayo sa pag-solve nito, or are you looking into, or are you seeing some additional examples for which this holds?
Actually, ang focus ko recently is yung sa 1 existence, because I feel like if you set this up in a good way, you can apply Schroeder-Brouwer's fixed point theorem.
Uh-huh.
Kasi parang ganun yung statement niya, no?
Mhm.
Then it has a fixed point.
Yes.
So nagpo-focus muna ako dito. Kasi I feel like may mga certain powerful results that you can apply. Although wala pa akong, may mga consider ako, no? Kasi ang issue kasi sa argument namin, two things. We use determinants, which is a very finite dimensional thing, no? Although there are ways to define it for certain classes of operators. But even though kaya mo yung gawin for certain classes, ang isa pang issue is compactness. If you really wanna use some sort of fixed point theorem. So they go hand in
Mhm.
hand, no? Kailangan may compactness, sort of.
Mhm.
So parang ganun yung nangyayari kadalasan. May isang condition na mahirap ipakita, mahirap malaman kung totoo or hindi bago ma-apply yung result. Another issue pa doon is continuity, no? Hindi ko na sinabi pero actually, hindi ko nasabi or hindi ko talaga sinabi pero hindi ko in-specify kung what type of convergence ang
Mhm.
in infinite dimensions, and if you're working with B of H, maraming topologies. B
Mhm.
of, ang hula namin is under the weak operator topology. Kung
Mhm.
finite dimensional, okay lang naman ng usual topology.
Mhm.
Anyway, yeah. So like I said, nagpo-focus ako sa 1. Maybe I should look at 2 and 3 again. Yeah. So I guess that's the recent development dito for me. No.
Okay. Thanks. So we have a question here in the chat box from Vickman. Hello, Kenneth. Di ko alam kung nabanggit mo na kanina. Saang fields nag-originate ang problem of matrix completions?
Over C lang,
Oversee.
like Banach spaces.
Sorry, hindi yung field na yun. I mean, mathematical field. Field of math. I assume may pinanggalingan yan na problem outside matrix analysis.
Oh yeah, yeah. Yung completion na concept, yeah, meron siyang marami applications, no? Depende dun sa prescribed entries. Meron siya applications sa biology, sa statistics. Hindi ko na sinabi kasi hindi naman ako expert doon. But yeah, certainly itong mga completion problems na to, lalo na syempre yung simplest version is kapag yung unknowns are just numbers, no? Of course, mas general to kasi matrices or operators yung unknowns. But yeah, for sure, meron tong applications, marami. Yung nagko-complete ka ng matrix na nagsasatisfy ng certain properties, no? Given given prescribed numbers. I don't know if that answers the question.
So, thumbs up naman si Sir Vickman. Okay, do we have any other question from the audience? Okay, so sa mga graduate students na maybe you find the problem interesting, so you can so may mga nabanggit si Sir Kenneth na mga open problems, so maybe you can send him an email or send him an email, if you're interested. So his email can be found at the IMath webpage. Okay, so if you do not have any more question, let us again thank Dr. De La Rosa for giving that interesting talk. Palakpakan po natin ulit siya. Let's give him a virtual clap. Thank you, Kenneth.
Thank you po.
Maraming
Okay,
salamat, Kenneth.
Yes, Mama Agnes. Okay, so our next webinar will be on October 25, and it will be given by, so we're scheduled to have 2 talks there, one from the optimization and approximation group and another from the differential equations group. Okay, so again, thank you very much for attending and listening. And again, thank you, Sir Kenneth, for that talk. Okay, so goodbye, everyone.
Thanks, Gino.
Thank you.